This conference will now be recorded.
Very good evening, students. We have been discussing current electricity chapter. So we have discussed electric current, Ohm's law, combination of resistors and cells, etc. So today, what we'll do, today we'll discuss very important and very interesting topic, that is electrical energy, electric power, efficiency of a cell, and if possible, we'll start Kirchhoff's law also today. So okay, so let us see what is electric power, like how do we define mathematically, also we'll see. Electric power so what is electric power? It is the rate at which work is done. See, electric power, first of all, this electric power is the power, sorry, the rate at which work is done by source of EMF in maintaining an electric current through a circuit is called the electric power of a circuit. Of the circuit or of the appliances connected. Of the circuit is more authentic because power drop across a circuit, we say, or in other words also we can say it is the rate at which the electrical energy is converted into some other form of energy, that is heat, light, etc. So that is also another definition of this electric power. Okay, so how do we define mathematically, or how do we express this electric power mathematically? See, if there is a circuit, suppose I have a resistor connected to a battery, okay, of voltage V, and this is R, say, and through this circuit or through the resistor R, current I is flowing. Okay, then what will be the work done? See, for this current is flowing for some time t, for some time t. So what will be the work done in this case? Work done excuse me. Yeah. So work done by the source of EMF or the battery will be, see if I say work done W, this we define as W, and like we denote it by W, so that will be V into I into T. So this is the work done. So once we get the work done, what is the electric power? We say electric power is denoted by P, electric power. Power is denoted by P, and that is W by T, just as mechanical work done, mechanical power. So this is VIT. V is the voltage across the resistor or voltage of the battery or EMF of the battery. I is the current through the circuit, and T is the time for, like, this is time means this is actually duration of time, and that divided by the time, so we get VI. So power is mathematically expressed as P is equal to VI. So this is actually electrical power. Now if somebody asks you what is the unit of this power, see work done is joule. Work done, unit of work done is joule, and see joule per second time. So this is actually a watt. Similarly, like similar to the mechanical power, etc. But see, in this case, in electrical case, we have kilowatt, and kilowatt is actually important. That is bigger unit. Even bigger unit is megawatt, 10 to the power 6. Kilowatt is, so let me, so kilowatt, megawatt, gigawatt also is there. So but the what is the commercial unit of power? Commercial unit of power. So commercial unit of power is actually HP, horsepower. HP in short, this is actually a horsepower. Okay, horsepower. And there is a nice relationship between horsepower and a watt. I hope you have been learning since your very early days, early classes like 5, 6 onwards. You're learning what is horsepower. So look, horsepower, HP, 1 HP is equal to how much? 746. 746 watt. 746 watt. So this is actually 1 horsepower, and this is actually see, in case of various machines, motors, actually we determine the power by HP. Various motors, okay, power of various motors. Okay, so commercial unit is HP, horsepower, and 1 HP is equal to 746 watt. And now what is electrical energy? So electrical energy can be written from here. See, work done is electrical energy, so that is VIT. Work done itself is electrical energy. Electrical energy is the work done by a battery to maintain an electric current through the circuit is called work done. And work done has as usual unit, that is, or energy has as usual unit joule. Okay, joule. But there is, okay, so I have, all right, I'll write. So this is electric power. Now electric energy. electrical energy, or electric energy also you can say electrical energy. So electrical energy is the work done or energy supplied by the source of EMF in maintaining electric current in a circuit for a given time. Okay, let me just write it. The total work done or energy supplied by a source of EMF in maintaining a current through the circuit for a given time. Okay, for a given time is called the electrical energy. Okay, and see, this electrical energy depends on the power of appliances used in the circuit. Okay, it depends on power rating. Okay, suppose there is bulb. Okay, there is a bulb and that is connected to a source of EMF or voltage V, and it ran for and it runs for time t. Suppose current I is flowing through the circuit. Okay, so V is the voltage of the source or battery. This is the bulb and it is running for some time t. So work done will be, and if the power rating or power written on the bulb is P, then work done will be P into T. So it depends on power rating. Okay, so this is joule into, this is watt into second. Watt into second means joule, but we have a very unique commercial unit for this, that is BOT. That is, see, this is actually, this can be written as watt hour, or this can be expressed as watt hour. Okay, watt hour or kilowatt hour. Okay, so this kilowatt hour is called board of trade unit. Kilowatt hour is called board of trade unit, and this is the unit in which the electric bills we get. Okay, 1 unit, board of trade unit, BOT. Okay, so this is actually 1 kilowatt hour. Okay, so kilowatt hour is defined as the electrical energy consumed by appliances of 1 kilowatt in 1 hour. If suppose an appliance has power rating 1 kilowatt, if it runs for 1 hour, then the electrical energy consumed by that particular appliance is called 1 unit, 1 board of trade unit. BOT, okay, board of trade unit. So board of trade unit, total this is called board of trade unit, and this is the unit in which energy consumed by our house appliances is seen in the electric meter. So electric meters are actually giving the reading in unit, that is mode of trade unit. Okay, BOT, 1 kilowatt hour. So 1 kilowatt hour, 1 kilowatt is actually 10 to the power 3 watt, and hour is this much. So how much watt, how much joule, sorry, how much joule you will get here? 3.6 into 10 to the power 6 joule. 3.6 into 10 to the power 6 joule. Okay, this is 1 BOT. 1 BOT is equal to, or 1 unit is equal to 3.6 into 10 to the power 6 joule. Okay, so now we'll move on to the power consumed by a series or parallel combinations of bulbs. Okay, so first of all, we'll see series combination of bulbs. What we are going to discuss here is, let me tell you, series combination of bulb. Sorry. Series combination of bulbs. So what we are going to do here, we'll see equivalent power consumed by 3 bulbs of different power rating. We'll see first. Okay, so let me draw the figure. Suppose I have 3 bulbs of different power, P1, P2. So let me draw, this is suppose bulb 1, then I have bulb 2, then I have bulb 3, and each of them has different power, P1, P2, P3 say. Okay, but they are designed such a way that they could be connected for working on the same voltage. They can work in the same voltage. In that way they are actually manufactured. See, okay, I think I have just skipped one thing. Let me tell you here, P is equal to VI, we have seen already. So we can apply Ohm's law. V is equal to IR again. V is equal to IR, so this will be I square R. In another words, we can write this R, or R is equal to P by I square. That we can do. Or from here we can see, I can write power in another way also. P is equal to V square by R. V square by R. This also we can do. That means power is inversely proportional to resistance, or vice versa. That is, R is inversely proportional to the power. Okay, so that we can write here. See, if I have 3 different bulbs, so P1, which has power P1, P2, and P3, they are connected in a series with the same voltage, same battery of voltage G, because they are manufactured in that way that they will be operated with the same voltage V. So look, what is the resistance here? See, power rating will be given like this. What is our power, and at which voltage it should be providing its maximum brightness, or at what voltage this could be operated. This is how power ratings in the bulbs will be given. So look, what will be the resistance of the bulb R1? That is V square by P1, right? V square by P1. Similarly, R2 will be V square by P2, V square by P2, and R3 is equal to V square by P3. Okay, so these are the three resistances. Now, since these bulbs are in series, they are in series combination, so equivalent resistance I can write R equivalent is equal to R1 plus R2 plus R3, like this. Now look, if I have equivalent circuit for this series combination where the same current is flowing through the circuit and the equivalent bulb is operated under the same voltage, then I can write this one as V square by P equivalent. Similarly, here I can write V square by P1 plus V square by P2, V square by P3. This gives 1 by P equivalent is equal to 1 by P1 plus 1 by P2 plus 1 by P3. Okay, so this is equivalent power. Okay, so equivalent power, or if I use an equivalent bulb, then that should have power this much. 1 by P equivalent is equal to 1 over P1 plus 1 over P2 plus 1 by P3. So in words we can say that for a series combination of appliances, reciprocal of the effective power is equal to the sum of the reciprocal power of each of the bulb. Okay, this is actually we can say. Now if there are if there are n bulbs of same power P, and they are connected in series, then what we get, 1 over P equivalent is equal to N by P. So this is actually the formula for effective power for a series combination of bulbs. 1 over P equivalent is equal to N over P when there are n number of bulbs of same, this is okay, this is all right. So I can write equivalent P equivalent is equal to P by N. This I can write. Let me just erase this part. Okay, so P equivalent is equal to, this is Q equivalent is equal to P by N. Now we'll see how do we define brightness. So brightness, okay, before that let me tell you how much current is flowing through each of them. Since they are in series, so the same current will flow through each bulb. Okay, through each bulb same current will flow. So what is that current? Current is I is equal to V over equivalent resistance. we had already written equivalent resistance this one. So this will be R1 plus R2 plus R3. So this will be the current flowing through each circuit, sorry, each bulb. Now how do we define brightness? Since current is same in each of the bulb, power in case of series combination is defined, sorry, brightness is defined by this I square R. So brightness of bulb 1 will be P1 is equal to I square R1. Okay, P2 will be I square R2. Then P3 will be I square R3. Okay, so these are the power, sorry, brightness. This is how we define in case of series because the current is same. So brightness is defined as I square R. Now let me tell you, if the resistance is more for any bulb, the brightness will be maximum for that. Okay, when they are connected in the same voltage, the brightness, see here R, we know R is inversely proportional to P, right? So this, with this we will connect it. So if the, see, since R is more if the power is less, okay, R is more, resistance is more when the power is less. So the lowest wattage or the bulb which has the lowest power, will glow maximum, okay, in series combination. You have to remember this, that R is equal to 1 over P. So if the power is less, then brightness is more. Okay, if this is minimum, brightness will be maximum, as the resistance will be maximum. So when the current in the circuit exceeds, so this is why when current in the circuit exceeds, this exceeds the safety limit, the bulb with lowest power will fuse fast. Okay, the bulb will fuse fast. Okay, will be fused fast, or okay, will fuse fast. All right, so now we'll go to the power consumed by a parallel combination. Okay, we have seen power consumed by series combination. Now we'll see parallel combination of powers, sorry, bulbs. Okay, so parallel combination of bulbs. See, let us consider 3 bulbs as we have taken earlier also. and all are connected in parallel combination. Okay, all are connected in parallel combination, and all of them are designed or manufactured to be operated by the same voltage. So this has power P1V, this rating has P2V, and this has rating P3V. This is the voltage. Okay, now see what are the resistances. R1 is equal to V square by P1. Okay, then R2 is equal to V square by P2. R3 similarly will be, this is V square by P2. This is V square by P3. So equivalent resistance in case of parallel combination, we know 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay. Now if we multiply V square left hand side and right hand side, V square by R1 plus V square by R2 plus V square by R3. Okay. So what are these? See, V square by this could be written as 1 over P. I'm sorry, this is V square by R. So this is P equivalent, then this is P1, this is plus P2, this is plus P3. Okay, this is the power. Okay, this is the power, equivalent power of the parallel combination of 3 bulb of different powers. Okay, so it will be just sum of the powers of individual bulb. Okay, so here if I have n such cell of, if n cells are connected, if n cells of power P, sorry, n bulbs I should write, n bulbs of power P are connected in parallel, combination, then the effective power will be, effective power of the combination will be P effective or P equivalent also you can say is equal to n into P. So this will be for n cells of same power. Okay, now we'll see what is brightness. Let me just remove this part. We have already learned what is P1, V1, P2, P2, V2, etc. Okay, so what is brightness? See, brightness here will define in terms of voltage itself, because voltage across each bulb is the same, right? So we'll define power is equal to V square by R. So in this case, see, power for the bulb 1 will be P1, so P square by R1, sorry, V square by R1. P2 will be V square by R2, what is written already here. Okay, so P3 will be V square by R3. So in this case, look, see, power or the brightness will be maximum. Brightness will be maximum which has less resistance. Okay, less resistance. So the brightness of the three bulbs, so as the resistance is highest, as the resistance is highest, okay, so since resistance, this is power, brightness is defined as P1 is equal to V square by R1. See, when the resistance is minimum, then the brightness will be maximum. So we'll again come back to here. So where the resistance will be minimum, where the power is maximum. If the power is maximum, resistance will be minimum. So as the resistance of the highest wattage is minimum, it will glow maximum. So I can write here as the resistance of the highest wattage. Resistance of the highest wattage is minimum. It will glow. It will glow with maximum. It will glow with maximum brightness. It will glow with maximum brightness. Okay. So this was with the power consumed by a series of parallel connection of or combination of bulbs. Now we'll learn another very important parameter, that is efficiency of a source of EMF. So how do we define efficiency of a source of EMF? So it is defined as the ratio, the efficiency of a source of EMF is defined as the ratio of the power output to the power input. Power input to the power input, okay, or input power. Okay, so it is defined as eta, or it is denoted by eta. So this is power output divided by power input or input power. Okay, let me write this as input power itself. Input power. Output power divided by, okay, so output power by input power. Divided by input power. So what is output power? If I have a battery, sorry, a cell of EMF E and having small internal resistance small r, and it is connected to an external appliances, say of resistance capital R, okay. So voltage drop, as you see the current, when the current flowing I, so V will be IR. This is actually output power. output power, and input power is, input power, I'll write V is equal to IR. This is actually at the output, not power. This is not power, this is voltage drop at output. This is at output and this is at input. How much this is? This is actually I R plus R. So this is at input. Okay. So power output or output power is VI, and this input power is E into I. Okay. Now again, this current is same, V by E epsilon, or E, sorry, this is E EMF, and V is equal to I capital R divided by I into capital R plus small r. So this is R by R plus R. Okay, so this is actually the efficiency. This is very, very important, and you'll see, we'll tell you there are few more things to discuss now. So this is efficiency. We can actually remember the formula. Eta is equal to R. R is the external resistance of the external circuit divided by small r, that is the resistance of the internal resistance, and plus capital R. This is actually again the resistance of the external circuit. Now, what is the maximum power theorem? We'll learn maximum power theorem. When the power will be maximum, power obtained from a cell will be maximum. So power theorem, maximum power theorem, it states that the output power of a source, output power of a source of EMF is maximum when the external resistance, external resistance external resistance is exactly equal to the internal resistance of the cell. Okay, so what does this mean? This means see, suppose I have a cell, same cell of EMF E, and it has small internal resistance, small r, small r, and the appliances has resistance capital R, and current I is flowing through the circuit. Okay, in that case, what will be the power? Power will be E square by R. R is R plus R, right? Sorry, output power means, okay, first I square R, say I square R, I square R. So what is I here? I is how much? Total EMF by total resistance. Okay, so if we put it here, so what we get is square by R plus R whole square into R. Okay, so let me do this simplification. Let me erase this part. So square R, and this part, see, R plus R whole square, this could be written as 4AB, 4 small r capital R. Because this I can write, okay, mathematically. So see, power will be maximum when, see, this is the square term, right, and that is in the denominator. So this cannot be negative anytime. Okay, that means it is always adding something to this. So if power has to be maximum, P max only when, P will be P max only when this R is equal to small r, or see, this term has to be 0. That's what I wanted to say. So this R minus R, this term has to be 0. That means R is equal to small r. Okay. So this is actually the condition for maximum power to be obtained from a cell. So internal resistance and external resistance has to be exactly equal to get the maximum power. Okay. So power, but then what will be the maximum power? What is the maximum power? P max will be how much? E square by, see, this will be 2R, then this will be 4R square, and this is R. So maximum power will be actually E square by 4R. Okay, or in terms of small r, also you can write E square by 4 small r like this. So this is P max. This is very, very important for NEET or JEE. Okay, E square by small, like E square by 4 small r, that is the maximum power. Now I'll tell you one more thing, that when the power is maximum, then efficiency obtained from, so I'll write this topic, when, or efficiency of a cell is 50% when power, when maximum power is delivered, maximum power is delivered by the cell, is delivered by the source of EMF, source of EMF. Okay, I'll tell you how it is. Eta is the efficiency, and that could be written as capital R by R plus small r, right? So this was the relationship. Okay, and into 100 will give you the percentage. Okay, now see, in case of maximum power, what is the condition? Maximum power will be delivered from a cell only when capital R is equal to small r. So this will be 2R. So this will be, see, if I write, this will be in, so this will be 50%. Okay, 50%. So efficiency of a cell will be 50% when maximum power is delivered from the source of EMF. So that is the condition. Okay. Now we'll see what is the efficiency see when when the source of EMF is shorted. Source of EMF is shorted. Shorted, that means you know what? This is source of EMF with internal resistance small r, and you are connecting this with a simple conducting wire. If this is the case, so this has resistance 0 almost, okay, and in that case the whole power will be consumed by this internal resistance, and the whole shorted, the whole electrical energy will be, the whole electrical energy will be dissipated as heat energy inside the battery, okay, inside the battery. If the external resistance is 0, then output power will be 0, and also the efficiency of the cell will be 0. Now we'll see output power from a source connected to an electrical motor. Okay. See, first of all, let me define. I think this is not the, okay. Now we are discussing efficiency of an electrical device. Efficiency of an electrical device. See, same eta is the efficiency. So output power divided by input power. See, this output power means output mechanical power. Output mechanical power and divided by input mechanical power. Sorry, input electrical power. Okay, this is the efficiency of an electrical device. So output, see, input electrical power could be actually a combination of output mechanical power plus power lost as heat. So this input power is actually utilized, or input power gets converted into input electrical power. Electric power is converted into two things: output mechanical power, plus heat lost. Okay, plus heat lost, power lost due to heat, lost due to heat. Now we'll see output power from a source connected to an electric motor. So in case of motor, We'll see this efficiency. Let us say the current drawn by the motor, is I. Motor is I. Then what will be the output, power output of the source? Power output of the source. So that is equal to P equal to EI minus I square R. The consumption by internal resistance we have to subtract. That will give you the output power. Okay. Now in case of maximum power, what we know? dp by di should be 0 for P max. P is equal to P max. Okay. So we can write left hand side is this. This is it. So P max dp, so this is 0, dp di is 0, and this will be 2IR. So from here we can see there is a relationship that I will be E by 2R. So here the current is E by 2R. Hence the power output of the source is maximum when the current drawn by the motor is E by 2R. So power will be maximum. Power will be maximum. Power output will be maximum when a motor draws a current equal to E by 2R. 2R. E is the epsilon, sorry, EMF of the battery. Small r is the internal resistance. Okay. So E by 2R. All right. So we'll stop it here for today. Next day we'll start with Kirchhoff's law. We could not touch this today. So next day, Kirchhoff's law and related numerical examples we'll discuss. Kirchhoff's law. Okay, so thank you for your patience. Bye for today.